Hi, good day, and welcome to the technical track of Oceanology 2020. This session is part of the imaging and metrology track within the technical sessions, and we're going to be talking about 3D image reconstruction. We have two chairs in this session. I'm joined by Walter Jardine, who is the Global Survey and Positioning Authority at BP. Many of us have known him for many, many years.
Hi, guys.
Myself,
Hi, folks.
I'm Keith Vickery. I'm with Zupt in Houston. We're all learning as we go through these interesting times. And this morning, we're joined by three great papers in this particular session. So I'll let Walter say hi, and then we're going to get on with the first paper.
Yeah, hi, good day, everybody. Welcome to this session with Keith and myself. Looking forward to it. As Keith said, I work at BP as BP's Survey and Positioning Authority. So I'm just going to hand straight back to Keith to introduce the first speaker.
So our first paper this morning, I'm sorry to be looking down and up, but you don't want the piece of paper I've got in front of me, in front of the camera. So our first paper this morning is from Andrew Speck. He's a principal researcher with Schlumberger. He's going to be talking to us about some really interesting technology in enabling, I would call it an AUV, he calls it a UROV, basically the next generation IMR platform. Andrew's got quite an interesting academic background and technology background. He's currently the principal research scientist in the marine robotics program at Schlumberger Doll Research. He's been in that position since 2018. He had a PhD from Harvard in low energy physics in 2005, continued working in atomic physics as a junior fellow at the Rowland Institute, joined Schlumberger in 2010, where he initially worked on novel downhole sensors for wellbore measurements, including in situ measurements of gas composition, prior to transitioning to the marine robotics program. I think you're going to find this interesting. I'm going to hand it over to Andrew, and we'll sit back and watch a very interesting presentation. Andrew, please take it away.
Great. Thank you, Keith, for the kind introduction, and thank you for the organizers for this opportunity to talk about the work we've been doing. I'm going to talk about work we've been doing to develop a new inspection, maintenance, and repair platform for subsea assets, and in particular, this idea of UROV, which is an untethered ROV. And here we're trying to sort of bridge the gap between AUVs, where it's completely autonomous with not much supervision, and an ROV where you have full control by a human, but there's lots of issues with the tether and costs. So I'll talk a little bit about how we're developing this a technique based on supervised autonomy, where the human is always in a loop, but the vehicle actually has some level of autonomy to make decisions at a low level. And we're trying to keep the human in control at all times. So right now, inspection, maintenance, and repair is usually done via ROVs, and where you have a fairly heavy support vessel, a tether for the power and communications, and then you send the ROV down and inspect these assets. You have a very high data rate with this. With a tether, you have a fiber link, you get more than a gigabit per second and low latency, so it's great for real-time control and real-time understanding of what's going on at that time. The drawback is that you have this tether, and you have to manage that, and you also have a large vehicle, large support vessel that increases the cost with lots of personnel on board. And so we're trying to be able to reduce that and eliminate that tether. And the way we're doing that is this idea of the supervised autonomy. And so we're going to start off with possibly a light support vessel or some level of resonancy that has the AUV. It dives down to the area you want to inspect. And then you can have an autonomous surface vessel, and we'll show some work we've done with XBlue with their DRIX as a surface gateway. You could also use the light support vessel. You don't need quite as big of one without this tether. And the way we're replacing the tethers, we're going to use high-speed acoustic links. So we have a downlink that can send commands to the vehicle, and along with acoustic positioning. And then we have a high-speed uplink, which is novel and has been developed in-house, which enables video transmission over these acoustic link. And with that, you can send both sensor video streams, but also sensor data. And that's what I will talk about today and how we've been enabling that. And the goal here, the issue here is that you still don't get quite the gigabit per second, but we're getting over 100 kilobits per second. And that turns out to be good enough for real-time video and really understanding what's going on with the vehicle and ensuring that you actually are having safe and reliable operations there. near these high value assets. You do have a bit of latency, and that's really what requires you to have autonomy on the vehicle. You can't really joystick the vehicle anymore because there's about 10 seconds of latency in terms both from the acoustics as well as other issues with video. And so you have to be able to control it sort of a higher level and say, go here rather than drive it there. And that's where we're spent a lot of time working on, is how to enable that. And the goal here is to reduce the operational risk with AUVs where you have no idea what it's doing. It's a sort of send it off and do something and hope you get the data you want. This is one where you actually in real time know that you're collecting the data that's needed. We'll reduce the cost of service by reducing the size of the support vessel and the number of people required. You can enable remote operations and other things with this technology. And hopefully in the long run, reduce the carbon footprint of these operations by reducing the overhead. So to show a little bit what this is going to look like, this is sort of more of a simulation of what would happen. But here the vehicle's approaching an asset, in this case, a Christmas tree. You can see down in the bottom left the UI that the human is seeing, that the operator is seeing at the surface. And here you have both in the upper right, you have a view of the camera, and then you also have this LiDAR image as it's scanning the structure you want to inspect. And by having this, you can have in real time really know what it's doing. You can optimize the sensor parameters if there's a problem, and you can also say, oh, I see something wrong, and go and inspect that and pause the mission so it doesn't just keep going, but you actually have an ability to say, I need to really look at this place closely if there's something out of the ordinary or worrisome. And so by enabling that, you really can have an ROV-like experience, but with the advantages of an AUV, and that's our goal. So moving on a little bit into the platform, this is a high-level view of what we've enabled. In the left, we're just showing sort of, we have sensors coming in, which is the perception of the vehicle. You have things like the standard sonars. We have multi-beam and side scan. We have a novel time of flight LiDAR that's provided by our partner 3D at Depth that gives really high resolution, sub-centimeter accuracy. We are developing a method where we can actually make temperature measurements of subsea structures in a flyby mode of operation. Based on the LiDAR technology again. We have a hydrocarbon detection sensor that looks for dissolved methane in the water, and we have the cameras on the vehicle. That all goes into the computers that are on board, and used both for the autonomy, so you can have robust navigation, you can do leak localization and surveys for leaks, and we're developing algorithms for pipe tracking, and this can go on. But you also have that same data goes into the client workflows and is stored using IVA software so that you can do the standard post-processing needed to deliver the reports to a client. On the bottom right is just showing a little more of what's actually on there in terms of sensors, and we talked about the sonar and the LiDAR and those techniques. We also have a number of acoustic devices. We have bidirectional acoustic telemetry that's low speed, that's mostly for command and sort of status updates. We have a standard USBL beacon, and then we have our novel high-speed uplink telemetry, which is what enables the video and sensor data transmission to surface. To look at it in a little bit better, clearer perspective in terms of how data flows, you have this sort of the sensors on the left. That data goes into our IVA software we've developed in collaboration with them, where it's merged with the navigation data, and that is really important because it means that now all the algorithms downstreams can work with georeference data. They don't have to worry about the fact that you have data coming in that is time reference rather than referenced as to where it's actually been taken in space. And so that's really one of the places we've spent a lot of time is building this middleware that allows us to enable advanced algorithms both on the vehicle, so all the robust navigation, the pipe tracking, etc., but also the situational awareness and the human in the loop piece where you have sensor QA, QC, you know that the vehicle's doing the mission you expect, and that's by sending the same data right up over these high-speed wireless communications. And then there's a path that goes into the data recording and the client workflows. And we really feel that this ability to stream the georeference data is a key enabler for any of these technologies going forward to be able to get real-time views of what's going on. So this is just showing a little more of the vehicle. It's based on the Saab Sabertooth platform, but we've enabled a lot more advanced functionality on top of that. And then on the right, these field trials, which I'm going to talk about, were done in conjunction with XBlue's DRIX. And you can see on the bottom the various acoustic transducers. You'll see the GAPS USBL, but there's also the high-speed telemetry link and a Sonardyne modem for the low speed. And so and we'll talk a lot about how this happened. We did a number of field trials in the south of France off of La Ciotat. So this is actually going to show a little bit of some of the results from this. This is video taken during that and back in last year, basically. This is just pictures of the Sabertooth and our UROV, getting ready for these trials. So here you can see the DRIX, and here's sort of a high-level view. And we have an operations vessel on the upper left. We had some client observers from third-party companies looking at this. Then you can see the UROV in the middle, and the demo and the DRIX off to the right. And then we have this demo site where we're using we're going to scan a World War II wreck of a P-38 plane that was used sort of as a nice target for these scans. And moving forward. So here the UROV is diving. So these were taken about 40 meters of water depth. This is showing some of the mission interface that we've seen at surface, where you can see in 3D where the vehicle is at all times, but you also have the feed on the right of the video, along with some status and health indicators. And so this is showing some of the ability, and this is a real live feed of the video. And we'll talk a little more about some of the other stuff down the road that we were able to do in terms of the sensors. So this is talking a little more about our ability to have this sort of situational awareness at all times. And so on the left, we have an integrated UI that has all the parts of this, both the mission planning as well as the mission execution and the sensor QC, which really enables an efficient workflow throughout a mission. So you have the ability to sort of control the mission, define it before the job, but also update it as it goes along and change it if you discover something. You have the ability to pull in previous bathymetry as well as the real-time sensor data to show where the vehicle is in 3D, along with any obstacles or other targets around it. You have up in the upper right the vehicle navigation and health monitoring, and then on the bottom right you have the real-time sensor data feed that is either the videos or the sensor that were sent over our high-speed acoustic link. Showing a little bit more what you can do with this rather than just showing video, this is actually showing the real LiDAR data coming in, and this is just a video of the sensor GUI running on the vehicle right now. We've now enabled it where you actually send the point clouds rather than just the video, but even just the video allows you to tell what it's doing. In this case, you could see as the vehicle dived that the LiDAR swath shrunk just as you'd expect, but it allows you to confirm that everything is working properly, and that's really important with any AUV where you don't have this real-time control, that you need to still be able to tell what's going on. Going into a little more on the sensors, we also did a lot of characterization of the LiDAR. This was taken, in this case, we actually went to a pool that's in one of our facilities in Norway, and put the 3D at depth LiDAR on the vehicle in that pool, along with also having a tripod mounted LiDAR, and we're able to compare that. And so in this case, we're comparing a compressor system that was there, and actually put some dimensional control targets, which you can barely see, which are these black and white checkerboards, where you can get a very precise measurement of the center of them. And by comparing those, we were able to show that we had 3 millimeter RMS accuracy even when the vehicle was hovering. So it's a very stable scan, and which also enables a very fast, where you don't have to set down and take a scan and then move the LiDAR and take another one. You can actually do it while hovering. The LiDAR also enables some interesting other ideas. In this case, you can actually look for bubbles in the water column. So as an idea to look for gas leaks, for example. And that actually looks like it is a very feasible option in conjunction with our hydrocarbon detector that looks for the methane. And so you can verify the methane is there with the hydrocarbon detector, but the looking for bubbles is much more efficient by looking out in space. We also compared these between the LiDAR and the multi-beam and some seabed scans. In this case, we just went over the same area of the seabed of the Mediterranean Sea at about 900 meters. And the difference between them was less than 7 centimeters. So we're really quite accurate. And we have all the lever arms and the data acquisition controlled to be able to take very precise scans at the sort of centimeter level. That was also confirmed by doing multiple dives over this P-38 rack. And in this case, we basically looked at the point clouds we got back and tried to register them and say, okay, how would you adjust each one to get them to line up properly? because that tells you a little bit of the reproducibility. And when we did that, we had sort of an RMS error of 0.8 meters in the horizontal and 0.13 meters in the vertical. And when you actually look at that, we only had at this time we only had standard differential GPS enabled, not RTK or better. And that actually is the GPS error you'd expect. And so with that, we're limited more by our initial position than anything going on in the vehicle and during the actual mission. And it's fairly easy to improve if necessary. Although at deep dives, that's probably just the USBL position uncertainty alone is in that range. So it's not clear that you'll get much better than that. So really coming to what this can do, this is showing some of the LiDAR scans. And in this case, we are actually taking these data rather than just hovering and taking a two-dimensional azimuth and elevation scan. This was taking line scans and moving and then stitching this all together. And so you get impressive detail in both, even in the 3D that you can't really get with multi-beam. You can actually see the propellers, and in a second we'll show a little more of a 3D view that shows these propellers very clearly. And so you can get 3D structures very clearly with this technique at high resolution. And then the bottom right is the video that we are able to take over a snapshot on the acoustic link. And so even there, it's quite clear at 100 kilobits per second. So as promised, this is the 3D points rotated around. You can clearly see these propellers and the other various parts of the wreck. And it's really quite impressive what's capable with when you combine sort of an AUV with high position accuracy with a high precision sensor like the LiDAR. So I guess I would like to conclude that we've sort of done a demonstration of this advanced perception on our untethered ROV platform, UROV. And it really it will enable IMR services that have the reduced operational risk, where you actually know what the AUV is doing at all times and you can trust it. It'll have reduced cost of service by reducing the manpower and the vessel footprint, and along with reducing the carbon footprint via those same mechanisms. And the field tests have demonstrated that we can support the fully autonomous operation without the tether. And we also are able to do this concurrent operation with autonomous surface and underwater vessels, where we link the position. We basically follow the position of the underwater vehicle with the autonomous surface vessel, so that you are always within the cone of operation needed for acoustics, and that's quite reliable. And then we've also enabled this sonar and LiDAR data acquisition with onboard, so onboard data streaming and an ability to stream the data up to surface, along with acquiring high quality surveys for delivery to operators. So thank you again, and I guess I'm open for questions.
Cool. Andrew, thank you very much indeed. I guess it's up to Walter and me now to ask the questions, because we don't have 55 people sat in our audience. Excellent presentation. I really, really enjoyed that. I guess the first question that comes to me, then I'm going to hand it over to Walter, is inspection, maintenance, and repair. I see the inspection bit. Is the plan to intervene into, say, some sort of torque tool, or intervene into some interface on a structure? You showed the Christmas tree, and in the interface face of the Christmas tree, is this going to interface into a structure and actually turn something, or is this truly just an imaging platform? The long-term target, I guess I'm just interested in what you think.
No, as you put out, right now it is just an inspection platform, but the roadmap is that we'd like to slowly enable more ability to interact with the structures. A lot of this would demonstrate the technology and demonstrate that we can safely approach structures closely, and then go into the next phase where you actually start to turn things and interact with structures.
In this fairly small platform with the onboard package you've got, I mean, most of these sensors are fairly current consumptive. What sort of duration, what dive duration do you have at the moment?
We have about 14 hours.
Okay.
There's quite a bit there actually is a fair amount of batteries on the Sabertooth.
Cool. Walter?
Yeah, well, I've got a few questions, probably three. Working for an operator, we always like to get our money's worth. So we'll see how we got on with these. I mean, maybe a fairly well, you would think a simple one to start with. I mean, Andrew, great presentation, some fantastic data, and imagery, and I think definitely the way the industry needs to be moving. So great news on that, and we know several, companies are moving in similar directions. Clarity on data formats. We've struggled historically with a myriad of different datas, and one of the ways of getting more efficient and better with things like AI is to standardize on data formats. Are you working in that area at all, or do you have strong views within Schlumberger of how you help to standardize in terms of the outputs from these types of sensors for the data and how you model it?
Yeah, and I think there's sort of a two-part question there. For right now, we've worked a lot with IVA, in terms of the post-processing and the workflow delivery. We've worked a lot with IVA, and so we're using their sort of standard data formats. I agree that yes, a non-proprietary format in the long run would be much better. There's a lot of advantages to that. And so that, I think there's places there, and we have some in-house ideas on how to, in terms of cloud-based platforms for processing and things like that we're slowly enabling. But I think that a foundation of open data is a really important part of that. On the second part, I think there's also a part in terms of open data on the vehicle itself, and we're trying to build data formats that are fairly interpretable and would be open to to sharing what the data structure is in real time, just to enable that and enable people to build their own algorithms on top of this, which I think is also important because there's the real time side as well.
Okay. And then maybe a follow-up on that one. I mean, I think we're obviously moving from an environment maybe 5-10 years ago where the data we were collecting for our integrity management teams was very visual or very physical. CP stabs, stopping frequently, getting lights under the pipe to see if it's spanning, etc., etc. We're moving much more to almost geophysical techniques. I mean, I see you seem to have a capability for side scan and sub-bottom profiler systems on board, and then obviously the LiDAR. So the data type that we're receiving is now quite different. Do you see that, is there a mindset change here or even a skill set change required by our integrity management engineers in order to change how we interpret that data or how we use it to manage anomaly detection? Is there a new skill required here, do you think?
I think at some point, or at least and maybe it's more back to the way the data is stored, going from where you get sort of notebooks and logs of, anomalies that are found to ones where it's sort of identified and tagged as to this is an area of concern. We did some work even on just recognizing anomalies in video and tagging it automatically using the modern AI and that style, just to reduce, part of it's also to reduce the brute work of just looking at all the data. To be able to give, here's the things you really want to concentrate on rather than look at hours and hours of video that is mostly fine with one anomaly once in a while.
Mm-hmm. Okay. Keith, I don't know if you got anything else you want
I
to
want to go down the rabbit hole of technology here. Your perception suite seems to be disconnected from your navigation suite. And in most current generation autonomous platforms, perception is part of navigation. So are you using any sort of feature detection and say monocular or stereo depth data from your imaging sensors into your navigation solution, or is it just a conventional DVL-INS, USBL type positioning solution at the moment?
As of right now, it is the conventional. We have done in-house work on registering point clouds between scans as well as with a priori maps, and I think that is clearly where it's going. There's a point where with a high end, and we have a high end fins system on this, you can get very close to the structure. So I don't think you need to really worry about the perception based navigation in terms of the navigating to get into the area where you want to inspect. It's then how do you get in close, and that's the switch between absolute navigation to something that's relative to a structure, and that's where we've worked quite a bit, is trying to start to build the algorithms that tell you you're 5 meters off from the structure and not quite aligned properly for the scan, to be able to adapt and sort of correct there. And that's really how we're looking at it, is almost a higher level navigation on top of the low level fins.
Okay, but so will you be using imagery to do that, or are you sticking with a LiDAR?
We think the LiDAR is probably, given the range advantage, the LiDAR in the Mediterranean, it's been demonstrated at 50 meters. I don't think in most cases we'll get quite that, but 10 to 20 is very feasible, even in semi-turbid water. And so that there's an advantage there to be able to see out farther, and then you get the precision. And so we're really going more and more towards, we'll use the camera to add sort of data to the LiDAR, but not so much as a primary solution.
Okay. The LiDAR data, just a quick point. I think actually David, one of our other speakers, has a question. Let me just finish up with another question on the LiDAR data. The trend in this space is to try and move towards automatic change detection, where we actually have the resolution in the point cloud data set, sort of a year-on-year survey or every other year survey, where we can use that data set to do automated change detection. Do you believe you have enough resolution in this LiDAR data to be able to do that?
I think, yeah, we are in the sub-centimeter accuracy and depth in axial range, and better than that if you're willing to hover in the other two dimensions, just because the scanning part is much more precise actually than the depth resolution.
Okay. David, you had a question.
Yeah, so just kind of following up on the some of the imaging discussion. So what are the options for the passive imaging, and how tightly do you couple that with a LiDAR?
In terms of we're doing quite a bit of work now on terms of using monocular vision and coupling that with LiDAR. One of the issues with LiDAR, point clouds in general is surface reconstruction is hard because it's hard to associate the points with the surface, and the camera provides quite a bit of information to do that. And so that's one of the places we're really looking at to be able to merge that. And there's also just merging the various sources of point cloud data into sort of one known map. And that's really the goal down the road, is to sort of combine all the sensors. They all have advantages, pros and cons and advantages there.
So is there a desire to paint what an RGB color camera sees onto the 3D reconstruction? Yeah,
and we're actually working on that. Yeah, because it's one of the things, the LiDAR gives you intensity of the green light reflection, but doesn't give you color per se. Right. And so there's some definite advantages.
One last question about that. So is there ever any issue with clarity in the scenes that you're looking at for the vision?
The water, the optical is definitely a problem in terms of being able to see. And yeah, there were ways to, we've looked at a little bit, and I guess, even with your polarization work, that there are some techniques to use that to look through turbid water. Turbid water is definitely a problem. Not so much in where we've done the field test. The Mediterranean is beautiful in terms of its clarity, but in other locations are definitely not that good.
I would suggest there's always issues with clarity when we actually get to real work sites. Got one final question, then I'm going to hand it over to Walter. So, and I'm sorry to be back down in the weeds, but so at the moment then you're not taking advantage of things like loop closure or bundle adjustment with any features that you're working with in the imagery. And I'm assuming the resolution isn't there in the LiDAR to be able to do that.
No, it would be doable. It's been a question of how necessary, and where we're at right now, the navigation solution is good enough that it isn't really necessary. We've done work on lower cost platforms with much lower end IMUs where we've tried to, and done that level of SLAM to be able to do loop closure. And then it's a question of, is it adding value, or is it almost creating noise? And so there's always that sort of two front way of, you either improve the sensor or you improve the algorithms around the sensor. And I think in the end, we'll end up having to do both to get a really, accurate solution.
Sure. Excellent, Andrew. Thank you very much indeed. Hugely appreciate it. I'm going to hand it over to Walter to introduce our next speaker.
Thank you.
Yeah, thanks, Andrew. Yeah, we definitely got our money's worth there. Some excellent questions and good conversation. So thanks for that, everybody. So we're going to move on to our second presentation now. This is from Stephen Labars, who has a subsea engineering background. He's actually now the Chief Technology Officer for IDOcean. He's going to be talking to us about ROV 3D georeferenced concrete armor unit seawall inspection. Now that's quite a mouthful, but when you see the size of the equipment and gear that they've been surveying, you'll see why it was such a long title. So Stephen tells me after an academic training in hydrodynamics and naval engineering, which he spent between France and Brazil, Stephen worked as a project manager in a commercial diving and marine works company in Reunion Island in the Indian Ocean. He then co-founded ID Ocean with Vincent McCain in around 2017. This is a subsea survey and engineering consultancy company that focuses on coastal infrastructure inspections and modeling with ROV and digital tools. And in fact, that's Stephen, obviously, what he's going to show us a bit of the work he's been doing, I think, actually in the Indian Ocean. So I'm going to hand it over to Stephen, and we'll hear what he has to say. Over to you, Stephen.
Okay, good day, everyone. I'm just going to share my screen. Here we go. Okay, so yeah, after the great world of the offshore oil and gas, I'm going to get you to the coastal engineering world where, well, we work with low-cost solutions, but we have also great ideas. I apologize for my English. Well, it's not my native language, so I try to do my best. I hope this will be okay. So yeah, just to introduce the subject, I'm just going to present you the work we've been doing over the past 2 years on the project in Reunion Island, which is called the New Coastal Road, which I'm going to introduce to you very quickly. So the New Coastal Road is a project from Bouygues and Vinci, which are two French construction companies in Reunion Island. So for those who don't know this, it's close to Madagascar and South Africa in the Indian Ocean. So the project consists in the construction of a 5.4 kilometer bridge on piles over the sea. So we are working a lot on this phase of the project for ROV surveys of the pile structures. But what will concern us on this presentation is the other part of the project, which is made of a 6.7 kilometer breakwater made of a concrete armor single layer unit, concrete armor unit, sorry, on a single layer. And then the road is constructed over this breakwater. And well, just to give you an idea, the breakwater, well, the shell is above 6,000 units per kilometer. And of course, it requires a lot of regular subsea monitoring to check the laying in the installation phase, and then also for extreme events like cyclones that we get not every year, but let's say one every 2 or 3 years here. So it's quite rough events. And then, well, what we need to control is any settlement on the breakwater, the laying conformity as well, for sure, and then some broken units. If, for example, there is a nose that breaks. Something you need to know about my presentation is that we are in tropical waters, so we get really, really good visibility most of the time. And that's why we can work with optical sensors instead of acoustical sensors, okay? So the classical method that were used by Bouygues and Vinci for the subsea inspection of the breakwater was to use divers. So what they would usually do is write on a slab before the inspection where they were starting and then where they were going, and then just follow the path until the waterline. But the problem with that is that they had no reference point on the seabed to know where they started. So they need to find, like with the bathymetry, something very easy to see underwater, and then identify and say, for example, this is P43 Acropod 1, and then from then they could follow. The drawbacks of this methodology is that during the inspection, they had no subsea positioning, of course. It was really long for the control engineer to check on which block he was seeing on the video. And then it was quite time consuming as well for the inspection. They would do around 110 meters of breakwater a day. And then we have a really special HIC risk also in Reunion, because we get shark attacks. This is not very common, but it was something that the client wanted to avoid. So he came to us and then asked us what we could do with our small ROV, which is a Blue ROV 2 from Blue Robotics, that we normally use for inland and port inspections. So he came to us and asked us if we could do near-shore inspections in open seas on the breakwater. So this was the first challenge, to check if it was possible for us to work on such say, harsh conditions in some time. What we discovered is that up to Beaufort 3 on the wind scale and HS 1 meter, and let's say current lower than 1 knot, we could work and then do a whole day of work. And then for the positioning, well, I had tried in the past several USBL systems on such configurations, but didn't prove to work very effectively because of the reflections due to the breakwater. And then we're working very shallow waters as well, between 0 and 4 meters water depth. So what we did is we tried a short baseline system from a Norwegian company called Waterlink, and then we mounted it on the vessel with a 2 meter distance between each receiver and varying water depths as well. And we coupled it with a HK GPS. And then what we got from that is that we had very, very accurate positioning, I would say lower than the meter, on 30 meter at each height of the vessel, which was fair enough for us in order to carry out the inspection. So on the software side, we just developed a small Python interface in order to get all the NMEA messages in the viewer. And then we did our own video quality improvement software as well to improve the deliverables. And then all the logs from the ROV were registered for post-processing the 3D position. And then, well, for the viewing in real time, well, we got the 2D position on the GIS software included in a PIP, as a PIP in a viewing software, which is called OVREC from Delta ROV. And then for the 3D visualization of the ROV in the laying drawings and in the project bathymetries, we used Fledermaus. Actually, we tried it in real time, but we had a lot of troubles with Fledermaus to do it in real time. So for now, we did it only in post-processing. And then we got the true heading, the true direction of the camera as well by combining the pitch of the ROV and then the tilt of the camera in order to always have a line that's pointing at the center of the acropod we are seeing on the ROV. So I'm just going to show you a small video that shows our results. It's back in 2019. Just get the sound, sorry. So yeah, it's quite old, and then we did some improvements since then, but I'm just going to show you that first. So what we see here is the video inspection. Well, this one's not that good because there was a lot of sun this day, where you can see all the blocks, and then the ROV is represented as a 3D model on the laying shots in 3D. And then this line is always pointing at the center block, which we see on the video. We did some confirmation tests with the client, and we were always pointing at the good acropod. So acropod is the name of the block that's on this channel, okay? And then what we could do as well, and it's really interesting for the control engineer, if you see something that's wrong, for example, on the bathymetry, then because the path of the ROV and the videos are time tagged with the same time tag, then he could just go back to the video and check what was going on the real video. And then otherwise, on the other end, he could do the opposite as well. So the result we got back in 2019 was, well, a good positioning accuracy for what we wanted to do. We reduced the time inspection as well. We went up to 170 meters a day instead of 110. Well, of course, we reduced and removed the HIC risk of shark. And then the control engineer earned a lot of time during the control process of the breakwater. So our next idea from there was to say, okay, now we have that. How could we get directly the acropod number, the unit number, overlaid in augmented reality into the video inspection? So in order to do that, I just skip this one. Yeah. Well, we thought we could use photogrammetry in order to recreate a 3D model of the blocks and then compare it to a reference 3D model on which we know the number of each block from the laying shots. But well, of course, in order to do that, we needed the 3D model of the whole shell first. So we developed an in-house algorithm that we patented since, and we call it C-beam, that enables to do a 3D digital twin of the whole shell. And then from this 3D model, then we can get the position. And actually, well, this was a co-product at that time that we wanted to develop, but we didn't see any commercial use for that. But now it's our main product, and we did more than 3 or 4 kilometer, 4 kilometer 3D reconstruction, and we created the digital twin of the breakwater on the new coastal project with this solution. So I'm just going to show you a quick video so that you have an idea of the solution. So this is as you can see, the aerial photogrammetry, the LiDAR data, and the multi-beam data of the project. And then what does the algorithm? It identifies automatically with 95 to 99% results, automatic detection, all the blocks inside the point cloud envelope. So instead of having just the envelope of the point cloud, then we get a 3D model. So this enables us to, of course, check contacts between blocks, check contacts with the sublayer as we have the 3D model. We can do through-time analysis to identify any settlements or movements of the blocks, of course. And the accuracy is in the limits of the accuracy of the bathymetry. So it depends, say, between 5 and 10 centimeters. So once we had that, then we took some legacy video from divers, actually, from a couple of years ago. And then we compared the photogrammetry that sorry, this is not this one, this is one. So we compared the photogrammetry we realized from the video. So we extracted all the pictures from the video, and then we compared it with the 3D model we had with the CBIM software. And then from that, then we can get the number of each block directly. Well, on this example, I embedded it directly in the 3D model, but I could have done it in the video as well. I have another video doing that, actually. And then you can easily identify. So this block here is the one with the cross. Here, over just above, you have another one. And it's quite accurate, actually. Well, we didn't do 3D model on the right side. That's why you are seeing on the left side here. And now, yeah, we could get on this with this method the accurate number of each block directly in the video, so that the control engineer didn't have to worry about what Aquapody was seeing on the video anymore. So for now, we only do it in post-processing. We are not able to do it in real time, as other companies might do it on other jobs, but we are willing to arrive there maybe in 2021. And then the last challenge we had is that in the intertidal area, because we're in Reunion, we don't have a lot of tides, actually 50 centimeters maximum, where we had no data. The multi-beam was absent, the LiDAR data was absent as well. So what we did is that we developed a photogrammetry process as well from a vessel and a stereoscopic system. And then we get the photogrammetry of the waterline that way. And since we have the photogrammetry of the waterline, then we can match this point cloud with the multi-beam point cloud, georeference it relative to the multi-beam in the LiDAR. And then from that, we can also recreate the 3D model of all our blocks that you would see right now normally. Yeah, here you get to see more clearly the 3D model we recreate from the point cloud. And you get to see on some blocks that we don't need a lot of points actually to find the blocks. The algorithm is quite robust to identify alone all the blocks. So I'm just going to go back. Yeah, just now on our further developments, this is where we are right now on this project. Further developments we are working on is to get the ROV position in real time through EVA modular ROV steering software instead of Fluidmos, because it's done that way. And we are working with EVA teams now to integrate our digital twin of the breakwater inside the software with each block integrated one by one, and then visualize the 3D ROV model directly in the modular software. And then the second thing we're working on, actually we're developing a USV, so a surface vehicle, on which we will include the positioning system and then the RTK GPS. And the USV system will follow automatically the ROV, so that we always have the lowest distance between the ROV and the USV. So we reduce the, we improve the accuracy of the positioning, and then we we don't get any jump in acoustics that we could get with a vessel that's not following the ROV, as it can't follow the ROV so close to the breakwater. So actually, it's a project we're developing with right now IFREMER, which is a French marine institute, in order to track turtles, because it's a marine conservancy project we are running with them. And then once we get good results for turtle tracking with the water link system, then we'll switch it to ROV tracking for breakwaters. Yeah, so I guess that's it. Thank you for your attention, and if you have any question.
Brilliant, thanks, Stephen. Yeah, very interesting. A lot of detail there. Thanks for that. I'm still a little bit shocked at the number of actual units that that project is installing. It's,
Yeah,
6,000 per kilometer. Is that what you said?
Yeah.
Wow. Okay. So a few questions just to try and kick things off. I mean, I was very interested to see the application of an SBL system. I mean, that's a technique that you know, many parts of the hydrographic industry has almost forgotten about.
Yeah,
we either seem to work
right.
LBL or USBL, and the element in between a short baseline system has been kind of forgotten about. So interesting for you to come up with an application that worked for you. I guess so that meant that the ROV itself must have stayed pretty much, or the vessel had to stay pretty much underneath, above the ROV. You had to keep the ROV within the four corners of the vessel, so that you were you had an internal solution for your SBL system, or could you excurт slightly beyond and still have a suitable geometry?
Yeah, we could go slightly beyond. Actually, we did several tests, and it's true that when we were too far from the breakwater, then we had too many reflections and it didn't work. But the good setup was to put the vessel around 20 to 30 meters away from the breakwater, and then from there, then the ROV could travel on say 60-meter area around the vessel, so 30 meters on one side and 30 meters on the other side.
Okay.
It was working very fine, and after that we got acoustic jumps. So
Yeah.
that's why we want to develop the USV now, and then make sure we always are just above.
Okay. And then just one follow-up. So I assume that means both for the surface vessel and also for I mean, it's quite a small ROV, and presumably that's where you were recording your multi-beam from the ROV. You must have had quite tight control on the attitude or inclination of both the vessel and the ROV to deal with the correction for you know, motion of both the vessel for the SBL system and for the multi-beam on the ROV. That must have been, and time stamping must have been really important.
Yeah, actually, we don't have any multi-beam on the ROV, so we only use the optical sensor of the ROV to recreate the photogrammetry of the breakwater. The multi-beam comes from a previous survey that's done from the vessel, like a classical multi-beam survey.
Right. Okay.
Yeah,
but that's is that after? Sorry, is that after the units are installed or before? No, that's after. Yeah, or before
actually,
and after.
Yeah, what the current organization is the following. Well, they installed all the units, and then the survey vessel passes, and he does the multi-beam survey, and then after that we do the 3D model with our C-beam algorithm, and then once we have the 3D models, they just identify the areas where they find anomalies, and then we just go with the ROV and check with our optical sensor what's happening underwater, and then we get the acoustic positioning.
Right.
Yeah.
That makes more sense.
Yeah.
Keith, you got some questions, maybe?
Yeah. A couple of questions. The update rate on the SBL system, it must have been, you're working in responder mode on the SBL system, so it's a fairly high update rate.
Yeah, normally I think it's well, I'm not sure about the reply here, but yeah, actually the transponder sends the pulse because it's linked through the ROV cable, and yeah, I'm not sure about the update rate, but it's lower than a second for sure. Yeah, I forgot. I'm sorry. Yeah.
No. It's just because you're in an SBL mode and you can work in responder mode. And you're such a short acoustic range, you could get a really nice high update rate with that configuration. Just practically getting those poles over the side of that small vessel, you probably learned some lessons about sort of tying them off and making them nice and firm. I mean, how did you physically deal with that? Because you presumably have to pick them up when you want to bring the vessel in and when you take the vessel out to move at any speed. It's bad enough putting a multi-beam pole over the side of a vessel, let alone 4 short baseline poles. was that a practical pain or was it easy to do?
You mean like I'm not sure I understood the question. If you just could
So
rephrase
a
it,
short
sorry,
baseline system, you've got 4 transducers hanging
Yeah.
over the side of the vessel.
Yeah.
Were they just hanging or were they on a solid mount?
No, actually we developed a solid mount for that. And then what we did is the vessel was not moving. The vessel was moored during the inspection so that we didn't have any any hydrodynamic force on the post. And then once we finished an area, then we switched to another area and then we just removed the poles from the water.
Pick them up and go.
Yeah. But that's why we
Okay,
want to introduce a USV instead as well, so that we won't have this problem anymore. Yeah.
Another one back to the ROV, and I think Walter raised the question. I'm just still interested. Heading. The multi-beam gets the data, and I guess you're doing a surface fit of like a shape file or a step file of these concrete devices to the multi-beam data, which is your CBIM algorithm. So you're doing a surface fit of a predetermined shape to the multi-beam. You're finding out where the anomaly is, where something's moved. Then you're going in with the ROV. Heading must be quite important for you on the ROV. On a small ROV, what are you doing for heading?
Well, we only use the internal IMU from the Bureau V2 actually.
Sorry, one more time.
Yeah,
Can
sorry.
you repeat?
Sorry. We use the internal IMU from the ROV. Well, we didn't get so much trouble with the heading actually.
Okay.
Yeah, because what we do is when during the inspection we are always facing the breakwater. So yeah, we didn't get in trouble with that.
And so I guess, and you're using the LiDAR to auto detect where you are in the model, as it were. I think is that how you then know where you are? You can fit yourself into the model by detecting the shape of each of the individual units. I think that's
actually if I just go back here, what we do is from the video we recreate photogrammetry of the whole area, and then once we have the 3D model of the structure. As well that we recreated with CBIM from multi-beam and LiDAR data. Then we just compare the two of them, and then we try to fit the photogrammetry that we recreated from the video onto the 3D model. And then since we have it, we can just geo-reference the video like that, actually.
Okay.
Yeah.
So you're not navigating in the photogrammetry in real time, you're collecting the imagery and then post-processing to show the anomaly.
Yeah, correct. Yeah, we don't know how to do it in real time yet. Well, it's a goal for sure.
A lot of people don't.
That will be very interesting. Yeah,
that would be good. Yeah.
Tough.
Yeah.
So I don't know if any of the Stephen, I don't know if any of the other presenters have any questions. I mean, if not, I have one more myself. I mean, I'm struggling a little bit to understand. I think what you said was each individual one of these 6,000 per kilometer units is individually coded, referenced, numbered. Is that correct, Stephen?
Yeah, actually, if you have a look, just go back here. Let me check here. So this is, for example, the laying pattern of one of the breakwater. It's actually 4 of them on the project, even 5, and then each breakwater is divided into sections. For example, here P43, P44, and into each section, each block has a name, has a number. Sorry, 1, 2, 3, 4, 5, 6, 7. So by combining the section and then the number, we can know exactly on which block we are seeing on the video. And then we know where we are.
And then you talked about auto detection of the unit number. I mean, I suspect this is going to be just too difficult, but I mean, would there be an option to, I mean, could you use QR codes on these blocks to make it easier to auto detect where you are in the future? I mean, it's an enormous task coding up every single one of these units, but they look like pretty expensive bits of kit anyway, and adding a QR code to them might be one way of being able to auto detect them. I guess you'd need multiple, so that it didn't matter which way they fell, you could always see at least one of the codes. But
yeah, that would be.
I don't know. Just a thought.
For sure. Yeah, that would be a good idea, and that would be doable. But yeah, that's something we need to work on with the conceiver of the blocks. It's a French company, so it might help.
Okay.
But
Walter,
yeah,
I'm just sorry. Just one quick question. Have you gone back to any areas yet where you've got any sort of significant marine growth? This looks like warm water. it looks like marine growth will take off quite quickly here. It will be really interesting to see how your structure modeling to imagery sort of manages when things start to get covered up with marine growth.
Yeah, that's true. Actually, we have a project that we're going to do by the end of the year. It's an old breakwater installed 10 or 15 years ago. It's full of marine growth, so we get to try that. But I'm really confident because since we have at least one nose of the concrete structure that we can see, and that's not full of marine growth, and we can recognize it. So I'm quite confident it will work. But it's something we'll try at the end of the year.
Yeah,
excellent.
Cool. Thank you.
Stephen, thank you very much. A really
much.
interesting presentation, a little bit different, which is great, and some nice techniques applied. I certainly, if I have any flood issues in Aberdeen in the future, I think I know who to come to for any flood protection options. I'm sure you can get me a couple of those units cheap, because there's obviously lots of them floating around. Excellent. I'm going to hand back to Keith before this gets any sillier, and let Keith introduce our final presenter for the day. Over to you, Keith.
Yep, thank you very much. I need some door stops in Houston. I think they'll do a good job as a door stop. Yeah. Excellent. That was really interesting. If you could hand the screen back, Stephen, then we'll move on to the third paper. Our third paper is going to be presented by Dr. David Chenault, who is with Polaris Sensor Technologies. He's going to be talking to us about infrared polarization, polarimetry for day-night oil spill detection. We have some interest in polarization cameras. Anybody that's doing some sort of 3D reconstruction in air or subsea is sort of moving towards the use of polarization in imagery, because it gives you a lot more observations, a lot more information than conventional RGB type imagery. So I'm really interested in this presentation. David is currently president of Polaris Sensor Technologies, where he's leading a team of engineers and scientists developing next generation sensors, including a suite of one-of-a-kind polarization imaging sensors. Dr. Chenault and his team support federal government programs, commercial customers for defense, intelligence, safety, and environmental applications. He pursued research and development in a variety of optical systems before founding Polaris in 2003. The great step of life where you walk off of stability into starting a company. I'm only too familiar with it. He has directed and directly developed a variety of optical systems, including the latest systems for oil spill monitoring, detection, and response. I'm going to hand it over to yourself, David. Looking forward to a very interesting conversation.
Okay, thank you very much. I appreciate the introduction. And yeah, I'm going to be talking about polarization. The polarization applications you mentioned are certainly applicable for 3D, but I'm going to be talking about a slightly different approach here. I'm going to be looking at thermal polarization, and the three dimensions that we're looking at are really on the surface, as well as the detection of the stuff on the surface. So the polarization is that we're talking about for this thermal camera is in fact the same polarization that we take advantage of when we're looking at polarized sunglasses with and with visible imagery that exploits that. In this particular case, though, the thermal actually relies on thermal emission, and the light becomes polarized based on the angle relative to the surface and the material properties. And it's it's really the material properties that we're taking advantage of in this particular application for oil spill detection and monitoring. The polarization is actually it's an additional dimension of the light that you're measuring, and so it does give you something else that you can detect. And one of the key features of that is that the polarization doesn't require any kind of thermal contrast. And I'll kind of beat this point home over and over again, that the polarization enables you to do detection when the thermal actually doesn't provide anything like that. And we don't need any kind of ambient lighting, and so it requires really only the thermal emission. We need something that has a temperature. And I'll show some examples of that. Now, it is important, though, that we do collect both the polarization and the thermal imagery at the same time, so we're not giving up the other thing. And again, you'll see many examples of that through this talk. So here's just one slide on how we do this. So we actually use a polarimetric or a microbolometer camera that has an extra polarization filter inserted into it. The polarization filter is actually embedded directly into the camera. So a lot of times people will ask, is this something that I can add to an existing thermal camera? That answer is no. It has to. It's actually tightly integrated. But what that does enable us to do is it enables us to do the collection of both the thermal and the polarization data at the same time, and in a very small package. So it's possible to put this on drones as well. So we've done a fair amount of testing with this, and both at test facilities and also a little bit of in situ testing in the real world, if you will. And this kind of summarizes the kind of testing that we've done. Day-night testing, we've looked at multiple crude oil and actually refined oil, both for gasoline and automotive oil and things like that. We've looked at calm water, breaking waves. We've done a fairly extensive study on where we are sensitive to it in terms of thickness. This is very important in terms of oil spill response, as well as in monitoring some type of facility. We've looked at pooling oil on sand and rocks, and we've looked at emulsified oil, and we've also looked at the action of dispersants on the oil in that detection process. And so just to demonstrate very clearly that we do detection day and night, we put together an experiment at the UMSET facility, which is the oil spill testing and research and development facility in New Jersey, run by the Bureau of Safety and Environmental Enforcement, BSEE. And on the side of you can see the pool itself in the top. That's the blue that you see in the left-hand side image. But on this, in order to do this thickness testing, we wanted some fairly uniform thickness samples. In the larger bin that you see, it was yellow that you could see in the visible image before things went dark. We have two smaller bins. On the left bin, let's see if I can show. So the left bin here, we had a uniform thickness of about 5 millimeters, which is really quite thick for any kind of oil spill or any kind of response activity. In the right-hand image, we're looking at 0.5 millimeter, so 500 microns thick. And in the imagery that we're showing, of course, we show the visible imagery over here on the left. It's nighttime, so there's no ambient illumination and it's dark. This is the thermal image that you would see with a standard thermal camera. And then on the right-hand side is our polarization data product. And in this particular case, the dark region is the detection. So now in this study, what we did is we, of course, looked at this imagery in a time-lapse manner over the course of about 18 hours from 3 in the afternoon to about 9 or so in the next morning. We're starting over here again. And so what we did is we looked at the contrast of the oil in the thick and the thin bin relative to the seawater that surrounds these bins, and plotted this contrast as a function of time. The blue shows the polarization contrast and the red shows the thermal contrast. And here, for example, around 8 o'clock in the evening, you can see that the thermal contrast between the oil and the background water is really quite low. The polarization contrast for both the thick and the thin stayed relatively constant and clearly superior to the thermal throughout pretty much the whole time. You may notice that we're seeing some polarization, dark polarization signature in the tank, and it turns out that there's residual oil sheens that are floating around in the tank that are being blown around throughout the evening, and that's what we're seeing in the polarization image. So the point here is twofold. One is that we detect oil at night, and two is that the polarization data product that we're measuring is really quite robust in terms of relative to the thermal detection throughout the whole period. So I'll go into the next one. So just to put a static image here, again, across the top, you'll see the visible imagery. The thermal imagery now is in this middle row, and the polarization is here. So there are occasions where the thermal, the thermal image shows that the oil can be detected when it's heated by direct sunlight, which you see here as the sun rose in the morning. So it is visible, but this is the 5 millimeter thick. The thin stuff really just isn't very visible at all. So one of the questions that we get a lot of times is how thick is the oil that you detect? So we did a couple of different experiments. This again is the OMSET facility, the big pool. In this particular case, we had an array of containers floating in the pool where we put in relatively uniform thick oil samples in this array, ranging from about 125 microns all the way up to about 5 millimeters. So again, with no oil in the middle to serve as a control. So you can see the oil that is relatively thin here is almost transparent. And the thickness is ramped up to the 5 millimeter stretch here. And we did, again, an overnight test of this. We did a time-lapse test of this. And we were able to see all of these thicknesses throughout the whole time period. So what we didn't learn was what the limit of our resolution is. So we went from 125 microns thick down to a bin that contained 10 microns. Now, it turns out that it's actually quite difficult to get uniform thicknesses in the larger pool. And so we reduced our test set down to much smaller bins in order to get uniform thicknesses. And so we started out with somewhere between 10 and about 10 microns and about a millimeter thick in these 4 data sets. And then we ramped up the thickness in steps in order to try to determine what our resolution is as well. And so the result is shown here. Now this is just a little bit of a scatter plot, but we started out with 0 and again added 10 microns all the way up to 120 or 1 millimeter. And then ramp that all the way up to over 5 millimeters thick. And so you can see our thickness response here. We have a peak in our response here that ranges somewhere between about 50 and 500 microns or so thick. And then there's a fall off that kind of asymptotically approaches somewhere around 1 millimeter. We can see that we get the same response. So another question that we get a lot of times is, can we determine thickness? And the answer is no, not really. We do get this enhanced response for the relatively thin oil between about 10 and 500 microns. But beyond that, we really don't see that. And this does depend a little bit on the angle that we're looking at. And so we really can't determine thickness, but we certainly clearly have a resolution in this. I call it really 50 microns is kind of what I quote as our standard threshold of detection. And this is important because this is about the transition from rainbow to metallic thickness, which is incidentally about where recoverable oil is. If it's any thinner, you really don't want to recover it. And so to show a few examples of both dispersant and wave detection, we did some tests where we threw oil into the OMSET tank in the presence of waves and looked at it over a period of time. And so you can see that the thermal detection that we see here, we actually see this very thin response here in the very thickness, very cool part of the thermal image. And this is what we call our E-therm image. So basically what we do is we take that threshold of detection and we paint anything thicker than that red. And so we can see that we do in fact have this kind of very thin detection that is enhanced around the edges. But we very clearly detect the oil that in many cases, actually in this case here, becomes difficult to detect in the thermal image. So in this case, this didn't have any dispersant image. We did a time series where we actually had introduced oil to the tank that actually had dispersant already mixed into it. And this shows the same time series and shows basically that the oil leaves the surface and the dispersant is very effective in this particular case. So it shows that we can actually monitor dispersant as it's applied to it. And this just shows the contrast and the detectability of that over the course of time. And the modulations that you see here are in fact the variation of our detection over waves. We also looked at emulsified oil in the ohmset tank, and by weathering the oil and agitating it with a wave action that we have access to with the ohmset tank, we're able to produce a very realistic emulsified oil that is very typical in an oil spill response. That ultimately ends up looking basically like chocolate pudding that you see here. And so we looked at that over in the same kind of context with a visual thermal or polarization data product in this E-therm. And so you can see that while it is very apparent in the ohmset pool with a very clear background, the thermal imaging is just undetectable really with the thermal. But that's in kind of a controlled environment. This is actually imagery that we took using the camera from a helicopter platform of the Taylor seep, the Taylor oil spill in the Gulf of Mexico. And again, you can see visually, if you know where to look, you can actually see a little bit of sheen. But what we're doing here is we're actually highlighting the oil that is, again, above this detection threshold and really represents the recoverable oil that you would recover in an oil spill situation. So we have taken this capability, and because we have shown that it is pretty robust in terms of the detection in all of these conditions, the day-night, the wave action, the emulsified oil, we've put together what we call pods, which is an autonomous detection system that exploits the polarization capability. And it some of the features that it enables is the fact we can do autonomous observation and alarming. And perhaps the closest connection that we have to the 3D aspect of the session is that we actually do have the potential to measure the area and report minimum volumes that are spilled, assuming that we have a little bit of a priori information, such as the height above the surface and the look angle and that kind of thing. But with the autonomy, we are able to basically do emails or texts or flashing lights or some other type of automated response that you might want to do either in a rig offshore or perhaps in a processing facility onshore. And we are able to support multiple cameras and do multiple detection zones. So this is an example of the autonomous detection. This was actually done at night, and so we had ambient illumination that we turned off there just a moment ago. And what we're doing is we're introducing a couple of ounces of oil into this, again, a detection bin. We have a handful of potential false alarms there. You can see as the oil enters the bin, the detection happens automatically. And in this particular case, we are talking about a specific camera location and the the emails and the texts are automatically sent out at the same time that our frame here shows detected oil. So moving on. So the applications, both for the camera and the autonomous detection, would include refineries, processing sites, transfer stations. We have shown that we can detect oil on land as long as it's pooling. If it's just soaking soil or vegetation, the detection isn't quite as robust, but if it pools, it certainly is. For oil spill response, there's initial detection and then of course overnight tracking and monitoring. We're actually responding to a spill up in Delaware right now for shoreline monitoring, and then for dispersant effectiveness, as I showed, in an oil spill response activity, we can help minimize the amount of dispersant that's applied. And so I think I talked about all this, so I'll just conclude and open it up for questions.
David, thank you very much indeed. An education. I guess my first question, can you walk us through the construction of the eTherm methodology? So it's eTherm, but it looks to me like there's some polarization information going into you painting red as well as the thermal information, yeah?
Yes, that is exactly correct. In fact, thank you for asking that. So this might be a good example to show. So the camera does measure both polarization and thermal at the same time. The introduction of the filter doesn't eliminate the ability of the camera to measure thermal. But it really just depends on how we process the data. The filter is placed on there on a pixel by pixel basis. So we can manipulate neighboring pixels in different ways. And so in one data reduction approach, we actually extract the thermal imagery. In the other data reduction approach, we provide this, or we produce this polarization image. And so what we're doing with this eTherm, which is an enhanced thermal data product, we do in fact use the thermal image as a background, because there is frequently interesting and useful information in the thermal image. But when we do have a polarization signature, again, the simplest way to think about it is just a simple threshold. If our threshold polarization signature gets above the threshold, then we turn that pixel red and replace the pixel in the thermal image with just a red pixel. And so that provides an indication of the presence of oil in that case.
In polarization cameras, you've got multi-angle data. In your instance, when you refer to polarization, you're combining all of those multi-angles into a final solution. Is that correct?
That is correct, yes. So, so you can indeed get angle information out of a polarization camera. In this particular case, our angles are usually pretty well set. They're pretty much horizontal in terms of the surface of the ocean. Now, what the camera does allow you to do, or what the angle information that we do get out of it, the camera is quite small, so it's smaller than your fist, and we regularly mount it on small rotary wing drones, or UAS. And so if the UAS pitches or rolls as part of its flight, then the polarization information changes slightly. But again, everything that we're concerned about in the oil spill detection application, everything's horizontal. And so the angle information, we just basically eliminate the roll and the pitch of the drone or of the camera orientation in whatever platform it's in.
So David, sorry, you're saying that you essentially assume that the sea surface is horizontal and you can rectify automatically on that basis, and that's good enough. Is that what you're saying?
That's correct.
Yeah.
Yeah.
Sorry.
Does that not impact your altitude of flying though? So if we're looking offshore, we've got a limit on the altitude we could fly to actually get the horizontal data into the camera.
No, really, we're not limited by altitude. Of course, the higher you go with a given lens, the larger the oil slick will need to be in order for you to be able to detect it. You're still limited by optics, but no, the polarization nature doesn't change with altitude.
Okay, I think Andrew had a question. I'm going to hand it over to Andrew in a second. He had a question.
Yeah, I just was wondering how, what's the frame rate like this, especially on these moving platforms? Is there a stability requirement to be able to process this, or how does?
Yeah, so good question. So we actually have two versions. One is a 30 hertz version, and one is a 7.5 hertz or frame rate version. Typically on drones, the 30 hertz version, the faster version, is what we use. But the data is collected in a single frame, and so the stability of the platform really isn't that big of an issue. The 7.5 hertz version, we use that when you're at a fixed site and things aren't changing very rapidly. It also makes it easier to export, as it turns out. But yeah, stability of the platform really hasn't been an issue for us.
In the size of pixel by pixel, in the bit depth of the pixels here, just so we've got some idea of one frame's worth of storage size or image size for export.
Sure. So it's based on the thermal cameras, and the currently available cameras have 640 by 512 pixels. And through this data reproduction, we can reproduce the entire frame, even though the pixels are kind of a checkerboard pattern. We can reproduce that entire frame for both the thermal and the polarization. Because it's relatively low resolution compared to multi-megapixel visible cameras you can get these days, the processing is done in real time. So if we mount this on a drone, the payload operator or the pilot actually gets any of these data products in real time, so he can view the scene in real time on the ground. We can also put the processing for a fixed site application. We can put the processing right next to the camera, and in a very small package, and provide the autonomous detection capability, and then provide a much smaller data package like a PDF of a snapshot that you can send over a cell signal or Wi-Fi or something like that.
But you're still talking tens of kilobits per second instead of megabits per second over a link.
Yes, that is correct. Yeah.
Okay, sorry, Walter, I think you had a question.
Yeah, I'm just interested, a couple of things, but maybe I'll come to the first one. So I might be off beam here a little bit, David, but you'll help me out if I'm wrong. So, I mean, essentially you've got this is a aerial imagery that's obviously off nadir, it's angled, which means in theory you should be able to ortho rectify that and use an affine transformation and actually map the oil spill and pull that data and map it into a GIS and show the extent of the spill and then monitor it as the slick moves. Is that something you've looked at already?
Yes, absolutely. So the area calculation that I talked about, we've matured that. We're almost ready to start testing that for fixed sites. When you're on a drone, it's a little more difficult.
Yeah.
Let me first say though that the reason that we look off nadir is because of the physics of the polarization. If you look normal at a surface, then there's no asymmetry there that produces the polarization signal.
Yeah, so you need the angle. Yeah.
Yes. Yeah. And so that's the reason we're looking off nadir. And of course, that angle, we can vary that angle from 5 to about 45 degrees and still get good detection. So you need to know that angle. First of all, you need to know what the altitude is. And,
Yep.
And if you have those two pieces of information and have them reliably, then yes, the orthorectification is a straightforward thing. In the smaller drones, getting those angles accurately is really just a matter of cost. You do need a good IMU that's mounted on your gimbal to give you that information, but it's absolutely doable, and we're headed down that path. That'll
yeah, that's really interesting. Yeah. So you can essentially map the slick and monitor it real time potentially, and particularly in areas where you might have fixed units, like in ports and harbors, as you say, or on refineries. You could actually it would be relatively straightforward because everything is fixed and measurable then to a high degree of accuracy, and you would actually have a standard format for how that off nadir image can be rectified and then plotted. Yeah.
That's right. Yep, that's exactly right.
Yeah, interesting. Keith, my other question was actually answered, so I've run out of questions, which is pretty unusual for me. So back to you.
I think I'm the same actually, Walter. I'd like to, unless anybody's got any other questions, begin to wrap this session up. I've learned a heck of a lot today, but that's not difficult because I don't know that much. It's been incredibly useful for me. I hope the audience find this session as useful. I'm going to hand it over to Walter for a minute to let him wind up, and then I think we're going to be done.
Yeah, and not a lot else to add. I do want to thank the presenters, some excellent presentations, and particularly in a slightly different environment. It's never easy doing this remotely, so many thanks for engaging fully on it. Great. So really just to confirm that this is us wrapping up the 3D image reconstruction session of the imaging and metrology track of Oceanology 2020. Thanks very much, folks.
Thanks, guys.
Thank you.
Thank you.